Hi, this presentation concerns problems of hardware verification and ways to solve them. Aimed at this point of research interest, C++ TESK and MicroTESK toolkits developed by our team will be introduced. Typically, hardware verification activities are subdivided into two global types, unit-level and core-level verification. In the first case, the microprocessor HDL model is separated into a set of particular units verified standalone where their input, where stimuli are applied, and output, where reactions are received, signals. Speaking about core-level verification, one usually means verification of not-separated microprocessor performed by means of so-called test programs, written in assembly language which the microprocessor HDL model can execute. Let's start from C++ TESK. Being written in C++ language, it supports development based on its component library test systems for RTL units and then their running and analysis of results. We'll touch upon some test system components later. Here you can see some screenshots of Eclipse IDE with C++ text syntax highlight plugin, coverage report example, control of distributed verification, a list of C++ TESK distributives available in forge.experts.ru some time ago. The test system according to C++ TESK includes three basic parts: stimulus generator set up by user-defined test scenarios, reaction checker including reference model and interface adapters, and coverage tracker measuring progress. To make matching and checking of reference model and target design reactions possible, interface adapters are used. Output interface adapters envelope pin label RTL model data into TLM messages. Input interface adapters unpack TLM messages and toggle RTL model input pins. Here is an example of calling, unpacking, and packing macros. It should be noticed that reaction checking cannot be done straightforwardly. In this example, reaction order of R1 and R2 is different in reference model and RTL design. Test system traces a bug, but what if there is no strict order on R1 and R2 generation, or the reference model is not so accurate to know that order? There should be a queue on each model interface, storing the reactions and checking their existence in the queue. This program is even more complicated, as reference model might know some partial order of reaction generation. To count it, C++ TESK uses complex scheme of two-level reaction arbitration. Returning to the verification of units, let's remind the task of stimulus generation. C++ TESK deals with it as follows. User-defined test scenario describes the function of current reference model state and the list of allowed by this model in the state stimuli. Stimulus generation engine explores such a graph defined implicitly, sending stimuli during the exploration both to the reference model and to the target design. Exploration can be done by several stimulus generation engines synchronizing with each other during their work. MicroTESK aims at core-level verification. It supports development of ADL description of microprocessors, defining possible test situations and test program templates. The generation of test programs is supported by the included library, which, using ADL description, solves constraints in templates and produces ready-to-execute assembly code. Here is a visual form of MicroTESK prototype, selection of dependencies between selected groups of instructions, setting of the folder to contain results. Typical test programs-based core-level verification means applying the same test program both to the target design and reference simulator. Then execution traces are compared with each other. Test programs from previous slide can be created as follows. One engineer develops a microprocessor model, another engineer defines test templates. Some engine solves the templates by means of the model, producing test programs in assembly language. Here's an example of some test program template with matching of test situations like overflow and generated test program with commands from MIPS instruction set. MicroTESK is an advanced program generator, so-called reconfigurable generator. The work of modeling engineer will be done by verification engineer only. This person, based on typical specifications with LDL-like style of instruction set description, can generate by means of LDL translator a model of microprocessor. Here is an example of LDL-like description of instruction add, which is automatically processed into a part of microprocessor model. Automatically, preconditions, test situations, and equivalence classes are extracted. Extracted test situations can be then used by the verification engineer in test program templates. Each test program contains of three main parts: initialization, test action, and checking. There might be dependencies between registers and addresses. Each test action covers one test situation for a defined number of instructions. Test program generation scheme includes selection of interesting operations, of test situations, of dependencies, of some parameters. To make a test program, generation engine selects a complex test situation for a defined number of instructions and creates required dependencies. Let the operations produce the following situations, and there is an address dependency. Engines takes the templates for each situation, makes a test program, and proceeds to the next complex situation. Both C++ TESK and MicroTESK toolkits can be downloaded from forge.espers.ru site. More information on the presentation subject can be found in our articles. Thank you for your attention. We're looking forward to your questions.